we discussed chapter 5, the forecaster toolbox, which is an introduction to some of the methods that we can use to understand how, the future values that we are predicting for the time series, different methods and also different techniques to try to evaluate the accuracy and also the effectiveness of that forecast, if it's unstable, stable, all the characteristics. Okay, and we mentioned that most of these preliminary methods are more baseline. In other words, it gives you a level so that you can see if your more complex models then can improve on that. If they don't improve, that means that your baseline is basically, the model that you should be using. There was one term that caught my attention, okay, and it's this term, random walk, okay, and I think it's important for us and for the benefit of the future groups to talk a little bit about that, because random walk is used in statistics, to describe a kind of process, what is called a stochastic process. So I went to the internet, right, and looked for some definitions in terms of random walk, right, just to try to understand better what we're talking about. Okay, let me go back. Okay, here we go. I just want to zoom a little bit. Okay, so this site is from QuantStart. This sites give you a very concise definition of what is a random walk. And random walk is, as it says there, is for time series modeling, happens when the current observation, the xt, let's put t, that's the current observation, is equal to the previous observation, but with a random step or down. In other words, it changes the direction, okay, of if it's going up or if it's going down. Okay, so this is the formula for the random walk. So you have xt. Let me see if I can. I cannot highlight it, but hit this one. This formula. It says xt is equal to xt minus 1, which is the previous observation, plus some direction. Okay, which is wt is a discrete value that is going to be mentioned as a white noise. In other words, it's a random value. So another definition that I found that is very useful also, okay, because this is more the statistical definition. But in this definition, which is from this site, Machine Learning Mastery, which is a very, very good site that has really good articles on everything about machine learning, it explains something about how can you determine if your time series follows the definition of a random walk. So it says here that some ways to check if your time series is a random walk is, for example, if your time series shows a strong temporal dependence that decays linearly in a similar pattern. In other words, you are seeing some trends, right? But sometimes you see, when you are in a short period, you see little, like little spikes, right? You can see the trend, you can follow the trend, but you cannot follow that short range. And the best example of this, of a random walk that follows a random walk time series, is a stock price, okay? When you see a stock price and you compare it, your current value from the previous value and then other previous values, you see that there's going to be a wobble, okay, in that stock price. In other words, sometimes goes up, sometimes goes down. But if you take, let's say, 2 years of that stock price closing, stock closing price, then you will see a trend, okay? And that's what it's saying here, that you can see in a long period, you can see a trend, maybe goes up, maybe goes down, okay? But you can see clearly what the trend is. But in a short period, let's say 2 or 3 days, you cannot determine with a level of enough accuracy which way it's going to go, because that particular process is more a random process. And it's called, in time series, it's called a white noise. Okay, so we're going to be, looking at that more, especially with the Google stock price that is included in that FPP3 library. And you will see that when you do an autocorrelation, a partial autocorrelation, you will see that the lags, okay, they really fall within the random area, okay, which is the dotted lines between 0, which is the area of not significance. In other words, we cannot determine if that lag is useful for predicting future value. Okay, and I think that's the important part of it, of the random walk, that for long periods you can extrapolate, or you can determine a trend, but for shorter periods it's not, the mechanism is not accurate. You cannot get an accurate observation, future observation from that particular period. All right, so let me put this in the chat, so it will go to the log. Okay, random walk. Definition. Okay, and then let me do this. Okay, is your time series a random walk? All right. And then going back to the book, it's interesting that the author is saying this about the naive forecast, the naive forecast, which is, the naive is basically taking the last observation and then extend it through the horizon period. That's the naive forecast. So it says that the naive forecast is going to be optimal when the data follow a random walk. Why? Because if this is a time series that follows the definition, the assumptions of a random walk, that means that the preceding value is not going to be a good predictor of the future value. Okay, so the only way that you can make sense of the naive forecast as a good forecasting tool is taking the last observed, because that's the only fact that you have. The rest, what you can do is just try to discern the trend of this time series. Okay, but with short periods, because they're random, you cannot say that previous observations can give you a good predictor of the future observations. So this says, because a naive forecast is optimal when data follow a random walk, these are called random walk forecasts. And this function, random walk, and you're going to see it in the drift function, can be used instead of naive. Okay. So I just wanted to make clear that point, because we're going to be seeing it more in the next chapters, especially with that Google stock price. Okay. So let's go then to the exercises. So Federica, did you choose one of the data sets?
Yeah, I did. Okay. I had a look at this Australian population.
Okay, so go ahead. Tell me the story of the Australian population.
Okay, so can you see my eye? Yeah. Okay, so this is the data set, global economy. And to start with, I was like a bit, I was searching on the FPP 3 package to find this global economy data set. I didn't find it. Then I did data and then global economy and found this data set is between this TST ball data. Okay, so I haven't said that. So the data set is made of some interesting information. We have different countries around the world, and obviously I have filtered the data set to be just Australia, because we are interested in analyzing, so having a look and predict future trends for the Australian population. And this data set is made of, as a country code, year. Years is a quite wide range because it starts in 1960. So it's a long time ago. And then we have information, the GDP, growth, CPI, imports, exports, and populations. Then I've made this vector myself. So I made GDP divided by population just to have a, I did a couple of plots and then to have a sensation of what's happening. And then we will see what I mean. So this is my new data set. I could just select the vectors that are of my interest, but you never know that you want to investigate other elements. But so the first play around that I did it was this is not shown clearly here. If I do data frame and then autoplot population, I have a quick look at the population immediately. So we can see that the population is increasing over time and is expected to be increasing. But if you are like a bit like looking on very little spikes that you can immediately more or less, because you know you have this continuous line that's growing within time. And it's quite perfect, you know, but it doesn't jump to your eyes immediately. These two areas here where things like had a bit of shake up changes, no? Okay, so it's a steady line, but if you want to investigate something, you know, you can say it's going to keep growing like that. Okay, this is the first thing you would. But then you will say, okay, yes, it's keep growing, but what if something happened? What's happened in the past that we can maybe take consideration of and see? So I like this two like little changes that the trend show. So what we can do? I thought, let's have a look about money, economical situations. So, you know, if it's an economy, you have it's struggling somehow, you do less kids, and so population can go down somehow. Okay, so let's have a look at this vector that I created, GDP divided by population, and let's put it across on the population trend and see what's happening. In order to do that, as they are different, so you see this is a different scale. Okay, so you need to scale the values. okay? In a way that they are the same, you can plot it, they will be on top of each other, and you can see how they differ. So in order to do that, you need to select the two interdiverse, select the two vectors, and then scale. And what you find is this outcome, okay? And the strange thing is you still have here, even if I didn't select here, okay? So I don't need this here in this way. So and this is not a data frame anymore, but it is a matrix. So I need to put it back as a data frame, and then I did zip bind with year, with the year vector, because the number of observation is exactly the same. So this way I had to call it like year 2, just, you know, and so here we have the years and everything. If I plot it, I do it fastly so we can see it. Okay, this is the result. So, and this red line is a geom smooth. So just to have a quick look at what are the doubts, where are the doubts effectively, no? Okay, this around right before, within the 2010, this bit here, and the previous bit was around here from 1975, around 1975. So, well, you might say, okay, why you stick on these 2 points when you have this whole bit here that is went down, but the population went steady, continued steady growing. Because I think this initial part, it's quite interesting, as well as the other one, because I'm interested in looking at the population changes, and these are the bits where the population changes. So as you can see here, there is a spike up of the GDP population, while the population went a little down, and this is the, and here they just follow exactly what's happened within the GDP population and the growing of the, exactly the same. So I think that this would be nice to have a look better. So what do you think about that? You have any thoughts, any insight? Maybe?
Okay. Yeah, what is interesting, because I'm thinking about the formula of GDP by population, right? So if you see an increase, right? If you see an increase in that number, the GDP divided by population, that could mean two things, okay? That the GDP is growing, okay? So because if your numerator is growing, then the value of dividing that by the population, it will increase. But also that value would increase even if the GDP doesn't increase, the population decreases. Okay, but since we are seeing that the population is increasing constantly, okay, it's basically a line, right? Okay, you can get an intercept and a slope, and you can get a formula, a regression formula on the population growth, because basically it's a line. So there are two things that are happening here for me. From let's say 1980, this is 1985, I say 1982, right? This point here, 1982, I don't know if you can see it, my mouse. From 1982 to 2000, let's say 987, between 2006-7, you see that the GDP by the population is below the line from the population. So that could mean that the GDP is not keeping pace. It's not keeping pace with the growth of the population. So you will see a decrease, right? From the standpoint of population. But then the reverse happens after 2007. Okay, withstanding that spike that you see in 2009. But from 2009, you see a really rapid growth of GDP, basically GDP population. And if the population is constantly increasing, that means that the GDP is really increasing really fast, okay, to get that number. But then it goes down. So you can see periods here where the GDP was growing at a smaller pace, the population, then other regions where the GDP was really picking up. In fact, it was kind of, galloping, and then it goes back, okay, to the and if I don't know if we can factor, because that's this data, I think, is until 2017. We haven't factored COVID yet, okay, in this data. So if we factor COVID in this data, then you'll see interesting things, especially probably the GDP will really go down, population will stay steady or go down a little bit, and then you'll see different interactions between these two variables. But this is good, yeah. It will be interesting, and we're going to cover that in the chapter 7 of tertiary regressions. It will be interesting is population is a good predictor of GDP divided by population. Okay, if there's a cross correlation there between these two time series. Okay, and which is the lag that is the most cross correlated to each one. Excellent.
So then let's model it. Okay, so I cannot see any trend. I cannot see seasonality. I cannot see, I don't know. I don't know what to do. So I've just tried 3 models, and then forecast, autoplot, and then see the mean if something shown. Okay, so first result is this. You see that the seasonal naive cannot be used, and we will see this why there's some reason, but we can use the drift and the naive. So they give
yes,
us
the seasonal naive, it won't apply here because there's really no seasonality. Okay, you have basically a line that goes up. Okay, kind of a monotonic. Okay, the only time that it kind of goes up and down is in that period. Okay, from 2009 to 2017. But probably that could be cycles. Okay, because seasonality is more in a shorter range. Let's say every 6 months, every year, etc. Almost to a year. But if you don't see any, sinus wave that you can see, okay, there's a pattern that I can associate by the seasons, by the quarters, or by half a year or a year. In this case, the time series is not, it doesn't have that pattern. So a seasonal naive won't work here.
As we introduced last week, so they gave us these 2 type of models. This way, they give us a benchmark. So we expect that real outcomes would be within these 2 model forecast results. As you mentioned about COVID, so here is not there is so let's just don't think about that for
yeah, because we know already what kind of what kind of effect, or at least we assume, what kind of effect COVID had on generally on the economy of the world, okay, and Australia is no exception. I will say that that forecast of the drift is too optimistic, okay? It's shooting up to the stars here, too optimistic, okay? So that's going to be basically the best case, that nothing goes wrong in the economy, the population keeps increasing, the economy keeps growing, at the pace of the last observations, and then maybe you will get some kind of future values associated with this. But we know with COVID that didn't happen, and COVID started around 2019 to 20. Then the naive forecast, remember, the naive forecast is the last observation. So we're going to extend the observation and then draw some confidence intervals. So probably this one also will be kind of optimistic too, because the assumption is that COVID really put a monkey wrench into the GDP. So we have to see the new values of the GDP to compare it to this forecast. Yeah. Okay, but at least it's a baseline. It gives you an idea of where your next models should be improving. All right.
Yeah. So let's have a look at this naive. Oh, which is so here we have some information. We have the residuals. Wait. We have this. We can see that they are not. They are quite skewed on the right. So we do not expect them to be normal, behaving normally. Even if that's strange somehow, because there is a quite monotonic growing trend. So you might expect that there might be spikes, some outliers such as the 2019, 2020, but you expect them to be quite manageable in some senses, so that they're very few spikes. You expect to find very few spikes, so that this is what. And then here there is the correlation, and we can see that they almost above the zero, and this gives some information about the lags, which is going forward, not going back. So it's all going forward. And so yeah, if you do the same with the random walk, I did the log of the population, you more or less find the same thing, except that this looks a bit more centered and less skewed, and you find that this is spreading towards, and there's more below the zero. What would you say? Would you add something?
Okay, let's go to the naive model on the residuals plots. Okay, in that lag, you can see those dotted lines. Those dotted lines that are equidistant between zero, upside, positive and negative, those are the significance lines. In other words, if the lags are within those dotted lines, they're not significant. Okay, So that means that the model that you're using is capturing that information on the lags, so the residuals are not associated with any significant lag. As you can see, because the naive only takes the last value, it doesn't take, account the previous values and just extended it like a, it could be a constant. You see that that lag 1, 2, and 3 are above that dotted line. So that means that that model is not capturing some information that is significant to the model. So for example, in a more complex model, you should try to incorporate those lags to see if you can get a better metric for your observed values and your predicted values. Okay. As you can see in the other one, the random walk drift model, this one is capturing more information because you see always 0. The first one is going to be up because that's the same value. It's going to be always up. But then you see the other ones, and there's only 2, that goes above. So that model, even though it's not the ideal model, is capturing more information. In other words, the more information the method captures, the more the residuals are going to behave randomly without any significant lags, and more or less they're going to have a Gaussian distribution. Okay, because the model is extracting the significant information, and then what is left is the white noise, the random walk. Okay.
Yeah, but going back where we were, okay, so this is the drift. The red one is the random walk, the drift. And this is the naive. So none of them is oh well, actually if we expect like a little drop down here because of some like world event like such an outbreaks of virus, and so we had the lockdowns and everything, but it not said that population keep going steady, growing up. So yeah, maybe this one here is the most suitable one, the random walk, which is the drift. Yeah.
Yeah, the only observation that I have with that model is that it's too optimistic. Okay. If I see this as the forecast for that measure, for that indicator, I would say that this is too optimistic because things happen, in the future that are not accounted for the data that you are using. And we had an extraordinary event, COVID, okay? And no one could have predicted the impact of COVID because the last pandemic that we had was 100 years ago, okay, with the Spanish flu. And that was an entirely different, economy, different social, configuration in every society. So what we only can do is predict with the data and the information that we have now. Okay, and we can make some assumptions, but that's all we can do. That's all we can do. So any model that tries to predict from 2017, that figure, the GDP divided by the population, that indicator, it was going to crash, with COVID. That's that's almost a given, a given, because the impact of COVID was too strong. Okay, it's an event that impacted, a lot of activity, economic activity that is associated with GDP and also health, health, a wellness that is associated with population also.
Yeah.
So it will be interesting to see the latest figures and then input it here and see how far we were from these estimates. But the drift, I would say that the drift is too optimistic. The naive, of course, is a constant, so that's only a parameter. And I will take it as basically a baseline, but it doesn't tell me anything. It doesn't give me any changes or anything. But that drift is too optimistic. is the best case, the optimal case.
Right. Okay. I don't know if you want to take the lead and yeah.
Yeah. Let's go for the bricks. The Australian bricks. Okay, so let's see what we have here. Okay. So I chose the clay bricks production data set that is from Australia, of course. That is from 1970, the first quarter, and then from 2002, the fourth quarter, the end of the 2002. And it's by quarters, it's by three months figures of clay bricks production. And as you can see, using the auto plot and the smoothing lowest a trend, we can see that even though there's a lot of ups and downs, okay, maybe some seasonality, etc., we can see the trend really clearly. So from 1970 to 1980, 81, that was the peak of clay bricks production. And then it went gradually, it went down, right? Down, 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 and then it stabilized here. Okay, so just seeing that pattern, if we're taking that previous observations can be a good predictor for future observations, I will say that this could be a low point, okay, in the clay bricks production, unless there's something going on that is changing the behavior of the market. For example, there's a new product that is replacing the clay bricks because it's less costly, or the material is more durable, etc., or it's easier to to handle, okay, because the bricks are heavy. So I have to research a little bit more about that, but just with the information that we have, I would expect that there will be an up in the production, and then again going down. Okay, according to this trend, not the spikes. I'm talking about the trend here. Okay, or maybe this trend will keep steady and then go down or go up. No, we don't know. We don't know yet. We need more information. That's what is good when we talk about the more complex models, for example, ARIMA, etc., that we incorporate other predictors, what is called external predictors, external regressors, to aid the model in identifying certain patterns that we have observed in the past. Okay, right now, the only data that we have is the date and the value that we're trying to predict. So, inputting those three models that we are using, the naive, seasonal, and drift, when we get the forecast, right? Okay, we put we fit the three models. We do the forecast for the next 10 periods, in other words, 10 quarters, and we do the we do the display. It means that, for example, in the naive, okay, in the naive, the value is going to be the last value, right? This value here, which it should be around 397. Then in the seasonal naive, I believe is going to be this value. Okay, the mean, because there's some seasonality hidden in that model that is going to be, acquired by the seasonal naive, and that is going to try to model that seasonality, okay? And then the drift is going to be the first value, the last value, make the trend, right? Okay, so it's going to take this value here, and this value here, and it's going to say, okay, this is the trend, and then it's going to extrapolate, that value. That's going to be the drift. So let's look at these models. Okay, we do the auto plot, we do the auto layer. This is from the book. And then we get those three, right? Those three predictors. As you can see, the naive is going to be the green. Okay, it's going to be here, around here. Then the seasonal naive is going to be this one, which is kind of the jagged one, okay, that is trying to incorporate the seasonality that is being reflected in that, past observations. And then I cannot see the drift here, but it should be around somewhere, okay? Yeah, I cannot distinguish, it's the red, it should be the red line, so it should be something around here, okay? So if we use the time tech and model time, which is packages that uses the tidy models framework for time series, if we recreate what we have been doing in the book, then we will have our table, right? The data set, with all this information. You're going to mutate the date as date quarter, as a date type. Then you're going to filter the data from those periods, because the other periods, they have missing values. Then you're going to convert it to an as table, and then select the components that you want, the data and the bricks, and then discard the quarter. And when you do that, in model time, you can do a split. So in other words, you can do a training, that you can split your data set into training, which is, in this case, is about 80% of your values, and then you can use the rest for testing. The benefit of that is that you can use the test to get those future values and try to see more or less, the accuracy and the fit from the models to the test data set. And then you can do, okay, this is the model that I'm going to use, and then you can use that for your forecast. So basically, this is more or less taking the tidy models framework and then adapting it for time series. All right, so we have the train, we have the test, we have our models. In the model time, there are only two models that are similar to the to the forecasting, which is the naive model and the seasonal naive. The drift model is not there, okay? But if you have time, you can customize. You can see the inner works of that model, and then you can customize, create it for that. But that's for another that's for another episode. So you get your two models that you have. You set the model, set the engine, the parsnip engine, and then you do the fit by the bricks by the date, and then with the data of a training, because we're doing the training first and then compare it with the test, with our unknown test data. So in the models, we're going to combine the naive and the seasonal naive. We're going to calibrate it. So when we calibrate it, what we do is that fitted model that we have in the train, we're going to then apply it to the test data. Okay, the model that we train already, apply it to the test data, and then we get a forecast, okay, a prediction for that test data. And this is the result here, okay? As the naive, as we expected, the naive is going to be just a line from the last observation, okay? You can see it clearly here, okay, from the last observation, which is, in this case, is 420. That's the last observation from the data set. And you see the confidence intervals. Then, in the seasonal naive, now you can see it clearly, is trying to capture that seasonality that is interpreting in the past observation. But as you can see, if you compare it with the actual values, okay, these are the actual values here. If you compare with the actual values, you see that there is an overfitting of the lowest values. Okay, the lowest values are too low here, and the actual values, they're really in this range. Okay, so that model is going to have problems identifying those low spikes. Okay, basically that's it. That's the exercise for the clay bricks production. Excuse me, using the FPP3 library, okay, from the book, and then adopting the same techniques except the drift, adopting it for the time TK and model time.
Right. Okay.
Good.
Yeah, that's interesting. Yeah.
Okay. So we still have some minutes. So
Yeah.
let me. I already started. Let me see if I can move this. Okay. I already started working with the chapter 7. So I'm just, to take the benefit of those. I think we have around 12 minutes left. Just do an introduction of chapter 7, and then we're going to dive in. Chapter 7 is a long one. Okay, it has around. It says here, we're going to skip chapter 6. Chapter 6 is more judgmental forecast, which is methods of developing forecasts both with non-mathematical models. It's a good reading, but I don't think we should invest time in that. We want to get more into the to the mathematics and the statistics and the algorithms. So this is chapter 7, is time series regression. Okay, regression models apply to the time series problem. And as you can see, even though there are about 9 chapters, they have a lot of information. So let's start with this. Okay, just a brief introduction, and we're going to be learning in the next session. So the learning objectives are the following. We're going to learn how to develop linear models with time series, how to develop useful predictors for linear models. We're going to be talking about residual diagnostics, which is important for the regression models because the regression models make assumptions, strong assumptions on the behavior of those residuals to validate your model. Then you're going to talk about selecting predictors and doing the forecast evaluation. And we're going to use some of the metrics that are common in the industry, RMSE, R-square, etc. Then we're going to do the forecasting with the regression. We're going to talk about a little bit about the matrix formulation, but that's more on the mathematical area. So probably we'll mention it, but don't get scared. We're not going to be doing calculus or anything like that. And then talking very important about correlation, causation, and forecasting. I can give you a preview that remember that correlation does not imply causation. Okay, in other words, if you have a good correlation of 2 variables, that doesn't mean that one variable is causing the other. And that's very important for time series because you can have different time series that are trying to help model your value, and you have to distinguish between the correlation and the causation. Okay, let me give you an example. Let's say that you are trying with a regression model, you are trying to predict the attendance of people for a year on a particular park. Since I'm from Orlando, let's say that Disney or Universal or whatever. Okay, So you will see that there is a seasonality there, but also you could bring information from the weather. So let's say that the weather is too hot or the weather is too cold. That probably will have an effect on the attendance figures of certain periods for the park. Okay, so you can extrapolate that some of the components of the weather are causing that they are correlated. But that doesn't mean that the weather is causing, the lack of attendance, because there are other factors involved, not only the weather, but you bring it as a factor that is correlated with attendance. Okay, got it there? We're going to talk a little bit more about that in the next session, but yeah, remember, correlation is not causation. Two variables can be really correlated and they don't have any relationship in them. Okay, all right. So just as an introduction, we have seen already our regression models, right? If we have, at least Federica, I know that we share the book club on the introduction to statistical learning, and there's a whole chapter on regression, on linear regression, multiple regression, and all the fun stuff. But in terms of time series, what we're saying here is that there's going to be a y value, which is the value that we want to predict, and it's going to have a linear, we're assuming that it's going to have a linear relationship with other time series x. So right now, there is a structure, okay, that we're talking about other time series. So your predictors are going to be also time series by itself. So you have to handle them with the time series techniques and tools to try to then formulate an equation that then goes to predict those y, observations, those y values. Let's take the case of that you brought of the Australian GDP exercise. We saw that apparently there was a good correlation between the population and the GDP divided by the population, right? Because you can see it visually. Visually, you can see it that there could be some dips, there could be some ups, but if we do the math, there could be a good correlation with that, and we're going to study that. That's called, in time series, it's called cross correlation, because it depends on the lags. Okay, sometimes just the time series by itself is going to have a number, but if you use lags for each of the time series, then you're going to see that some of the lags have a greater correlation than the time series at lag 0. Okay. Okay, let me see if I have more. Okay, so just 2 minutes more. So this is what we're talking about. In the simple linear regression that we have an observed value and a predictor, okay, y and x, you're going to have this kind of situation where you have an x, okay, with certain values in sequence, and then you have y with other values in sequence, and you can draw a line, a fitted model, a line, where what you're trying to do is minimize the errors. That epsilon figure, the one that the distance from the observation to the line. You're trying to get the best fitted line that is going to minimize the least squares, the least squares between that distance. And that's what it gives you. That linear regression model is what it gives you, is the best line that is going to minimize those errors to the square. Okay, so let's finish here, because then we're going to get into the example of the book, the US consumption expenditure, etc. So, but right now, this is some of the things that we have to keep in mind. That regression models can be applied to time series, okay? In the simplest form is going to be an observed value Okay, let's say park attendance. And then let's say X could be the weather. Okay, or it could be the date also in particular, because the date, depending on the season, there's going to be major attendance or going to be low attendance. Okay, and correlation is not causation. Remember that. Okay, record it in your mind. Correlation is not causation. Correlation is not causation. Okay. All right. So basically that's it. So we're ready for chapter 7. Okay.
So have a good weekend.
Huh? What was that?
Have a good
Okay.
weekend.
Have a great weekend. Yeah. And so we'll see. I hope that the link appears. The Zoom link appears next week, because I don't know if John, then there's
The link
something
appears.
to not scale it. But if it appears, I'll be there. Because remember that our changes not this Sunday, next Sunday. So we still have next week at the normal time. Okay. In fact, it's going to affect me more than you guys, because you're in Europe. You change later. All right.
Okay.
Okay, so I'll see you next week. We're going to finish chapter 7, and then we're going to do some of the exercises.
Thank you.
Okay. Take care. Ciao. Ciao.
Ciao, ciao.